Today's topic is the talk about mode compensation methods to reduce the shrinkage. Okay, this is the outline for today's presentation. And the first one, I will talk what is the warpage and the warpage types. And I also summarize the root cause factors to the warpage issue, and also to demo some case study for solving the warpage problem. And the last one, I will utilize our Modex 3D software to evaluate the warpage problem. Okay, so what is the warpage? So the definition of the warpage is warpage is a distortion where the surface of the molded part do not follow the intended shape of the design. So that is the definition of the warpage. Okay, so the warpage problem is always from the molding residual stress. So this kind of the residual stress is caused by the different shrinkage of the material in the molded part. Okay, so there are three common factors to produce the warpage problem. The first one is the temperature difference effect. So the imbalanced cooling channel design is a common reason to cause the warpage problem. So in this picture, you can see the 4 cooling channels are placed at the bottom of the part. However, only 3 cooling channels at the top side. So the hotter temperature accumulated on the top of the part. So therefore, we can predict the part is deformed to the smile shape, just like the picture below. The next one is the packing effect. And the gate location and the gate size determine the packing condition of each area. So in this picture, we can see the pressure is gradually decreased to the end of the part. So the imbalanced pressure pattern might cause the higher shrinkage at the end of the part. Okay, so the last one is the part orientation. Okay, part with the fiber material is a good method to resist the warpage problem. Okay, so in this picture, we can see the fiber is aligned with the flow direction. Under this condition, the shrinkage rate along the flow direction becomes smaller. And reversely, the shrinkage rate is significant higher than higher along the transverse direction. Okay, so in this page, I showed you the warpage types. The first one is the linear shrinkage, and the flatness, and the roundness. So the meaning of the linear shrinkage is the material deforms along the linear direction. So the calculation way is maximum displacement divided by the part original dimension. So the mathematical calculation way is shown in here. Okay, so the flatness, the part flatness is defined as the rise level or indentation level compared to the original surface level. So this is the meaning of the flatness. And the last one is the roundness. And the major tool is also popular in the Modex 3D software. And the meaning of the roundness is how closely the shape of the object approach that of a mathematic perfect circle. So we can see the picture here. So the outside of the circle is the perfect circle. And after demolding, your part might be deformed, like the ununiform shape. So how to calculate the roundness? I show you the formulation here. The roundness, the maximum roundness value minus the minimum roundness value. Okay. So this page, I summarized the potential root cause factor to induce the warpage defects on the part, and expect the page can give you the more ideas to solve the warpage problem. Okay, so normally there are 4 key factors which could produce the warpage issue. The part design, the mold design, the process, and the material. Okay, so for the part design part, the usually problem we meet are the imbalance thickness distribution. And the next one is discontinued structure in the part design. Some part design has the steep transition or rib and bolt structure in your part. That may, if your design is not very well, it might be a root cause factors to cause the warpage problem. And the incorrect using timing of the metal insert. Okay, so the next one is the mold design. The uneven cooling efficiency might cause the temperature difference of the 2 sides of part, just like I showed in the last page. And this kind of temperature difference could cause the part warps to the hotter temperature side. And the gate location and the gate size and the gate numbers are the important elements to control the warpage problem in your part. Okay, so the next factors is the process. For the process condition, among all the molding process parameter, temperature and the pressure are the 2 important factors to influence warpage because the 2 factors directly related to the material shrinkage, just like the PVT behavior, materials PVT behavior. So in general, a reduction of the shrinkage can be achieved by lowering the melt temperature and increasing the packing pressure. And also we can extending our packing time to solve the warpage problem. So if you have some experience to work in a factory or to work in a practical injection machine, you will know sometimes we will extend our packing time or packing pressure to solve the warpage problem. However, if you extend this kind of a time, it will rise your total cycle time. So you need to balance you need to find a balance between them. So if you have some experience about DOE, design of the experimental, you will know that DOE is a very good method to find out a better process parameter in your case. So the last one is the material. So amorphous material or semi-crystalline material have different influence on the warpage problem. In general, the amorphous material is less influence on the warpage problem compared to the semi-crystalline material because for the amorphous material, it doesn't have the TM point. For the semi-crystalline material, we need to take the part cooling rate into our consideration because crystalline material has a sharper transition caused by the crystallization during the cooling. Okay, so if you have the materials PVT curve, you can find the curve shows the totally different behavior between the crystalline material and the amorphous material. And also the fiber orientation is also a considered factor to cause the different warpage behavior. Fibers tend to align in the flow direction, especially in the area close to the mold wall. So shrinkage along the flow direction of the fiber orientation is relatively smaller. And if fibers are aligned well, the shrinkage along the long axis becomes smaller. If not, the shrinkage will be similar in the both direction. So you need to understand your flow direction in your mode. It can help you to predict the warpage behavior after demolding. And the last one is the fiber content percent. And for this part, I will show you one case study to illustrate how fiber content percent can help you to improve your warpage problem. So I think this page is very useful for you to find out the root cause factors for warpage defects. Okay, so here are a few quick examples to demonstrate how those factors cause the warpage issue in the MODEX 3D simulation software. So the first one here we can see is the thickness. In the left bottom is the thickness. And after slicing the model from the MODEX 3D software, we can see the volume shrinkage value inside the part. So the thicker section have a larger volume shrinkage than the thinner region. Because heat accumulates more easily in the thicker region, it is more difficult for cooling to reach the middle area. So in here we can see the thicker region has a higher volume shrinkage because the heat is difficult to dissipate. So therefore, a well-considered part thickness is an important point to prevent the product warpage. Okay, the next one is the insert. So in general, the part shrinks isotropically with a small deformation. We can see in this model. The left one is without the insert, and it shows a smaller warpage problem. However, if our part add one insert, the insert restrains the shrinkage on the bottom half. So the part warps significantly upward instead. So this is not a very good time to add the insert in this case. Or maybe you have to change the insert location in this part. And for the gates here, the original design has 4 gates, and the length from the sprue to the gates in each are not equal. Because the gates are small, the packing effect generated from each gate is different and leads to the serious warpage problem. So the amount of the shrinkage can be reduced by enlarging our gate size and also to adding more gates to create the equal length of each runner. Thereby the warpage condition is improved. So you need to think more detail about your part design to make sure each length from the sprue to the gate to your part is the same. It is the better way to prevent the warpage problem. And also, if you want to have a very balanced packing efficiency, you have to make sure you have a very adapter gate size and the gate numbers. And the last one is the fiber. So if material without a fiber in this picture, we can see it shows a larger warpage. However, if our material with the fiber, our material has fiber, it shows the small warpage because fiber is an inorganic material and it can help us to resist the warpage. Okay, so now I'm showing you some case study, and the case study is from our customer, and it can be published. So the first one is the front cover, and the front cover is utilizing in the laptop. And in this case, we change the gate design and to see if the gate design can help us to improve the warpage problem. Okay, so this is the case information. And the objectives for this case is to improve the warpage problem with different gate design pattern. Part name here is the laptop cover, and dimension is here. And the material we used is the PC plus ABS. And this is the process condition. So it's a raw design, and we can see it has the hot runner and the cold runner. and the part. Okay, so this is the first result from our simulation, and this is the melt from time, and the time at the 20% time stage, at the 50%, at the 70%, at 100%. Okay, so from the melting flow pattern, we can predict some problem from this picture. At the 70% time stage, we can see the two melting flow might converge in this here, in the red circle area. So it might cause the wheel line or air trap in this region. The other problem of the road design is the stretch marks. And the stretch marks appears on the gate area. And stretch marks is not very good for your product appearance. The deformation along the three direction, X, Y, and the Z directions of the role model. So the objectives for this case is to improve the warpage problem. So now we can see the warpage value of the role model. So along the X direction, the deformation is about minus 2 millimeter to the 2 millimeter. And the Y direction is the minus 1.5 millimeter to the 1.7 millimeter. And the Z direction is about minus 1.45 millimeter to the 1.2 millimeter. And this kind of a value cannot be accepted by our customer because it is the laptop. It is the front cover for a laptop. So we need to find out the methods to decrease the deformation value. We optimize our original design to like this. Upper right, you can see the optimized model. We increase our gate numbers and we change our gate location. So from this melting flow pattern, you can see at the 70% time stage, the melting flow becomes better than the previous design, and we can predict the melting will flow to the end of the part. So it can reduce the wheel line and also can prevent air trap on our part. This is the comparison between the two kind of the design, the raw model design and the optimized model design. So the wheel line and the air trap might cause in the raw model, just like the picture here. And for the optimized model, the melting flows to the end of the part is an ideal situation. The most important things in this case is the deformation value. So we can see the deformation along the three direction. The first direction is the X direction, and the deformation is from the minus 1.3 to the 1.3 millimeter. And if you remember, the previous design is about minus 1.9 to the 1.9. So the design is very helpful for decreasing the warpage problem. Not only X direction, but also the Y direction and the Z direction shows a very good pitch value. If we consider if we just consider the Y direction displacement, we can see the total deformation value for the raw model is about 3.2. And because we plus from the minus to the from the negative value to the positive value, so we plus the two values together, so it will the sum up is 3.2 millimeter, and for the optimized model is about 0.5 millimeter. The conclusion for this case is the melting flow behavior of the raw model could cause the obviously wheel line on the part surface and the air trap. And the second one is the optimized gate design can efficiently reduce the part displacement from the 3.2 millimeter to the 0.5 millimeter. And because I cannot show you the practical product, in the practical product, the results shows the very obviously wheel line in the raw model. But after we change our our gate design, the wear line is decreased, and it doesn't show the air trap on our part surface, and also it improves our warpage problem. So this is the first case to talk about the gate design can help us to improve the warpage problem. And for the case number 2 is talk about an automotive system. And in this case, we change our part design. We added one part insert in this design in order to get the balanced thickness and the balanced temperature. Okay, so this is the case information, and the part name in here is the side window encapsulation, and dimension is here, and the material we use is the for a part is the PVC. Okay, so we can utilize our Modex 3D software to measure the cross section of the part, right? And in that time, we measure the cross section, and we find the average thickness in this region is the 10.28 millimeter, but the thickness deviation is the 3.18 millimeter. The 3.18 millimeter is too high to be accepted by our customer. This is the geometry design for this case, and there are 4 part insert. The first one is the aluminum insert. If you can see, it's the picture here, and the transparent glass and the glass round channel. And our part is the PVT encapsulation. Okay, so this is the cross section of the part, and you can see the PVC encapsulation is on the upper of the product. And this is the round channel. Round channel is the glass round channel is this one, the yellow one. And the transparent glass is the orange one. Okay, so this is the first result from the simulation, and this is the cooling temperature. And if you can see, you can find the heat is accumulated at the thicker region, which could cause the warpage problem, just like I showed you in the previous page. I showed you many root cause factors to cause the warpage problem. The uneven thickness might be one factor to cause the problem. So cooling temperature range is from the 48 C to the almost 200 C. So we can see this temperature bar here. So the huge imbalance temperature pattern might cause the warpage problem. Okay, so this is the results for the X direction displacement before the optimization. So along the X direction, the range of the warpage is from the -2 millimeter to the 5 millimeter. So here shows you some animation. So we can see the total displacement is about almost 7 millimeter. It's a very serious problem for our customer. In order to modify this problem, in order to solve this problem, we modify our geometry, and we add one insert in this design. So the left one is the original design. The original design doesn't have the ABS insert, but after modified, we add one ABS insert in order to get the balanced temperature pattern and the more balanced thickness pattern. Here I showed you the comparison between the two designs. The maximum temperature in the cooling stage is decreased from the 200 degrees C to the 150 degrees C after we added one insert. And we also can see the temperature range is also decreased. So for the original design, the temperature range is the 50 degrees C to the 200 degrees C. But after we modifying the design, it's from the 50 degrees C to the 150 degrees C, which means that it is more, we got the more balanced temperature pattern. Okay, so we also compare the deformation, because the customer want to reduce the serious warpage problem, and the value is about 7 millimeter. Okay, so for the rod design, the displacement along the x direction is about 7 millimeter. But after we plus one part insert, it becomes 2 millimeter. So we succeed to improve this problem after we plus one part insert. Okay, so this is the other direction to see the results. Okay, so we can see the animation, and the animation in the rod design is shows a very serious warpage problem. And after optimized, we can see a very huge difference between the two designs, and see a very good performance on the optimized design. So in conclusion, for this case, in this case, the part insert provides not only good warpage resistance along the x direction, but also much balanced temperature profile. And also, the most important thing is we improve the displacement along the x direction, decrease from the 7 millimeter to the 2 millimeter, about 70%. Okay, so the case number 3 is talk about we change our cooling channel design and to improve the warpage problem. And the case number 3 is a rifle stock arm brace. So this is the case information, and the material here is the TPE. Here is a picture of our part. Okay, so this is the temperature difference in the mold and in the part. Okay, so for the original design, just looks like here. This is the raw design. The cooling channels design looks like here, this, and the conformal cooling design looks like it. Okay, so we compare the two designs and to see the simulation results. So this is the cooling temperature of the raw design, and we can see the cooling temperature of the raw design. The highest point is about 170 degrees C, and after we modify it, it decreased to the 95 degrees C, and also the temperature range is also decreased. Sorry, the temperature bar is too small. You cannot see it, but it's almost from the 95 degrees C. The range is from the 95 degrees C to the 160 degrees C. And for the more temperature difference, it also improved a lot after we change our cooling design. For a raw design, we can see the highest temperature is concentrated on the part backside. Here, the red region. But after modify the design, we can see the highest temperature is about 27 degrees C. The important thing for this case is also the deformation, especially for this part, the red circle part. Okay, so the original displacement for this part is 1 millimeter. And after we change our cooling channel design becomes 0.3. Okay, so the conclusion here is conformal cooling design provides good cooling efficiency to release the heat accumulation in the part, and the cooling temperature is decreased from the 160 C to the 95 C after we change our cooling design, and the temperature effect displacement is improved about 70%. Okay, so the last one is the back cover, and it's also utilized in the laptop. And we change our fiber content for this material to see the fiber content. To see the fiber content is important factors to the warpage problem. Okay, so the objectives for this case is to improve the Z direction displacement less than 1 millimeter. And so the part name is the back cover, and then the material is the PC, polycarbonate, and the part insert is aluminum. So this is a practical production. And the thickness for the aluminum and the plastic is the same, 0.5 millimeter. So this is the layout of the runner and the cooling channel. So from this layout, we can see it also using the hot runner system and the cold runner system. This is the results of the Z direction wattpitch result. And for the original design, the wattpitch value of the raw model is from the -5 millimeter to the almost 3 millimeter. So we can see it's a very huge wattpitch problem on this case. So the total wattpitch value is about 8 millimeter. So in this case, we utilize the fiber to improve the wattpitch problem. So the original material here is the PC, and the substituted material is the PC plus 10% glass fiber, and also the other one is the PC plus 40% glass fiber. So here shows you the results of the wattpitch along the Z direction, and the PC plus 10% glass fiber shows the total displacement value is 3.2 millimeter, and the PC plus 40% glass fiber, the total displacement value is the 0.61 millimeter. Okay, so here shows you the practical picture, and it shows you the simulation to help you to understand the real situation in this case. From this table, we can see for the original material PC without the fiber, the wattpitch value is the 8 millimeter, and for the real case, it also shows the 8 millimeter. So in conclusion, the part with the higher percentage of the glass fiber is a useful method to solve the wattpitch problem. The Z direction displacement is decreased from the 8 millimeter to the 0.6 millimeter. Okay, so the next section shows you a video and teach the newcomers how to measure the wattpitch in a more dexterity. So here just show you the video. Okay, so the first step here, we have to open your wattpitch results and to click the total displacement and to use the measure distance. To use the measure distance function and to select the 2 points you want to measure. So in this case, we select from the left to the right. And click the save and close, and you can see the original linear shrinkage. The original linear shrinkage is the 1.9%. And please don't forget to turn on the all direction. And you can choose the anisotropic or isotropic. And to enter the value for the y direction 1.25. So after you enter the 1.25, you can find the value from the 1.9% to the 0.66%. It's a kind of a compensation. And after you compensate your model, you can export the deformed model. And to make sure the safe name and the safe location, so you can start exporting. Okay. So summary. In this report, we summarize the potential factor which might cause the wattpitch problem on the part. And also in the case study, the main factors to cause the wattpitch are the gate design, part insert, cooling channel design, and the fiber percentage.